Right. So yeah, um, this week we're working through something called volume of revolution. I suppose, volumes of revolution. So the idea is that you take a two-dimensional shape and you rotate it about an axis, and so that's going to give you a volume of revolution. And you can change what axis you rotate around. So it could be the x-axis, it could also be the y-axis, it could also be something that is off-axis. So something like x equals 3, for example. And those off-axis ones are a little bit more tricky. So I suppose we'll have to talk about those a bit more carefully. But the idea is that there's actually like two different ways we can approach. Well, there's two different setups for these types of problems. And well, there's the disk or washer method. And so that's one method. That's one way of thinking about it. I want to signify that like these two things are very related to each other, and so you kind of want to just think of them as the same thing. Really, the idea like a washer is just a disk minus a disk, so it's very related. The other method is something called shell method, which I think in the lectures is something that's covered a little bit later, and in the homework it'll actually be the second half of that. So, but the thing is that like if you're just arbitrarily given a problem, you're not going to know whether it's disk or washer method or if shell method is the more appropriate method to use. But the way that the problem looks is going to dictate what method actually applies better to the situation at hand. Some cases you can actually apply both methods, but usually you can tell that one method will stick out as being more usable than the other. But the first thing is, well, the formulas that these two methods involve. So, well, maybe I can try to draw like a picture and try to illustrate as well. So let's say that you had this kind of a shape. So that this part that's shaded is the region that you're rotating. You're creating a volume of revolution. Okay. What happens that makes this a disk or washer method? What you want to do is you want to look at a segment of the region and think about what that traces out. So if you take that red line and you rotate it about that axis, that's going to trace out a circle, a disk. So that is what makes you recognize that this is actually a disk or washer method. Versus if you instead had, and this is where it's a little bit less typical because in this way, rotating about this region, it kind of doesn't make sense to do this. But if the red line was like this and you're rotating it about this axis, then what this does is it traces out a cylinder, okay, what we call then a cylindrical shell. So that's why this this image prompts that you to think of this as the shell method, okay. But so what happens is that these two-dimensional pictures are just illustrating actual three-dimensional objects, and we want to figure out like the volume. Okay, so the formulas that would create the volume are something like, let's say this is from A to B, and then this is, actually we don't want to, I don't want to label f of x, and I don't really want to label A or B. I kind of just want to write this in the abstract, and you should understand what A and B are. Okay, so in the case that we're talking about disk, and this picture illustrates disk, you have some R function, R standing for radius. So you want to think of this function as symbolizing the radius of that disk that you would trace out. and you just integrate over that from A to B, where A and B are obviously what the x goes from and to. Okay. And it's not just r, it's actually, you want to square the function r, so maybe I'll put that in parentheses and square the whole thing, okay? So this really looks like pi r squared. You're just taking a bunch of circles and then you integrate over them, you sum over them, okay? So that would be disk. And now what happens to make this more like washer is if instead you, maybe I'll just draw completely, well, a mostly new picture. What happens is instead you have like that as your region and you're still rotating it about an axis. But what happens this time is when you trace out this, let's say maybe red is still something that shows up a little bit more clearly. So this, when you trace it out, it's going to create something that's in math we would call an annulus. It's a circle, it's a disk with a disk removed, and then you're summing up all of these things. Okay, so this would be the actual region that gets traced, and well, maybe you can anticipate what the formula is going to be. It's going to be the big radius squared minus the small radius squared. And then we just integrate over that. So we really want to think of this as being a disk minus a disk. So that's what this formula is effectively doing. Okay. And I'm going to also explain shell because I think it makes more sense to introduce both of these approaches at the same time so that you can then try to grapple with the concept of how can you tell which method fits for the problem. That's usually the stumbling point for this section, I would say. Okay, so shell method, the formula is a little different. Well, quite different, I would say. So instead of pi, you actually have 2 pi, okay? And instead of just taking a radius and squaring it, what you're doing is you actually want to calculate, it's a bit tricky to explain this, but because you're summing up these the surfaces of these cylinders, okay? And so that's why the formula ends up being a radius function times normally in the textbooks, this would be denoted as a height function. So for this, I really do want to actually label, I think. So usually we wouldn't use this picture. We would instead, the normal way that you think about a shell is that you're rotating it about this axis. And maybe you still have the same kind of function, but in this case, the segment that you consider revolving is that piece in red. So now it's vertical. The important thing to note is actually whether the segment that you're rotating is parallel or perpendicular to the axis that you're revolving. So the key thing is that in disk or washer method, that segment is perpendicular to the axis of revolution, whereas in shell, it's always parallel. That's really the way that you tell these things apart. So, okay. So now let me label things. So r of x is the radius of a cylindrical shell, and h of x is the height of the cylindrical shell. So those are the two things that you need to pick apart in your cylinder. Maybe I'll draw the cylinder here just because it kind of looks a little bit better. So it would go like this. Okay. And so, yeah, you need both of these components. And I'll say that it gets a little bit more tricky when you're off axis because then things might be a little counterintuitive. I don't know, but there's definitely a problem that involves that we'll cover on Thursday, I would say. And you can let me know if you are confused by that one when we get to it. Okay, are there any questions on on this explanation of the disk washer shell? If not, well then let's start going through things. Okay, so pretty much I always start by drawing a picture. It's very useful to see like what the region is that we're talking about. So yeah, we have a line and we have like 3 bounding lines, it looks like. Okay, so if we sketch this, no, that's not so good. Straighter. X equals 0, x equals 2, and y equals 0. So y equals 0 is kind of like a base. And then we have 1 here, and we're going to go up. And we want to revolve this around the x-axis. Okay, so this is approximately what the figure looks like, and we're going to revolve that. Okay. Well, using the formula, we would have pi integral. The bounds of this shape are going from 0 to 2, so because those are actually given to us in this problem. So we go from 0 to 2, and we want to square the radius function. So now, visually, you can see that the radius of the disk is going to be the height, or it's going to be the function, the upper function that we have. So this 2x plus 1. So we want to square this guy. And that's it. If we calculate this integral, we'll get the area. So that's a straightforward computation, which I guess I can go through part of it. Obviously, you want to square this out first. 4x plus 1 dx. And then you want to integrate this guy. I don't know. Do you want me to like go through the integrals in detail? Because I mean, it would fill up time mostly. Someone wants me to. Okay, fine. Yeah. So yeah, this is just power rule. We integrate it. So this is going to be 4/3 x cubed. And this is going to be x squared over 2, so we get 2x squared plus x. And then we would evaluate this thing from 0 to 2. Right, and so now I'm just going to refer to my previous calculation. So when you plug in 2, you're going to get 62 over 3. When you plug in 0, you're going to get 0. And so your final answer is 62 over 3 pi. Something like that. Yeah, okay. I don't know. I don't know where to put the pi. That's kind of the bothersome thing for me. I don't know what's the standard way you write that. All right, number 2. So volume of a solid rotating the region. All right, we've got a line and a parabola. 10x, just say that that's 10x, and a 2x squared. So you kind of know, like, yeah, they're gonna intersect somewhere, and it's gonna be about figuring out where. So, well, the way you do that, you set the 2 equations equal, you solve. So this is gonna give you that x is equal to 5. And so this intersection point is at 5, and you have this region, which I guess I'm gonna shade, and then I'm gonna also, oh, I should also denote we're revolving around the x-axis. And in this picture, like, it would make more sense to consider this segment. Okay. Yeah, eventually, I think one of the problems later we do, yeah, the next one, we have to think about things in terms of the y-axis. That's fine. So yeah, so here, this is our segment. And when we rotate this, there's a gap, right? There's a gap from this lower function to the x-axis. So this is actually a washer method situation. Okay, well, so the integral that we set up, we've got pi times, Well, the integral is going to run from 0 to 5. It's going to be integrated over the x-axis. By that I mean, like, you can think of that red line as sweeping through from x equals 0 to x equals 5. So each one of those is going to give you a washer, and then you're just integrating, summing up all the areas of the washers. Okay, and we want to square the big radius and then subtract off squaring the small radius. So the big radius in this case is the line 10x, and we want to square the parabola. Okay, and well, we can just go ahead and compute this thing. So first I want to simplify the inside. 100x squared minus 4x to the fourth, and then I want to integrate this. So this is going to be 100x cubed over 3 minus 4x to the 5 over 5, evaluate from 0 to 5. And well, when we plug in 0, we'll get 0. Still, it's nicer to show a bit more work than that. So yeah, but then let's see, plugging in, what did I get? Okay, so I just got a number, 5,000 over 3. So yeah. So I mean, yeah, I don't want to do the arithmetic mentally. You have to raise 5 to the 5th power, which 625 times 5, and then times a 4. Whatever. That's what you get when you calculate it. Any questions so far? Yeah. Okay. All right. So yeah, number 3. So this time it's a bit funny. It looks a bit funny because we have x is equal to y squared. That's different from usual. But you should know what that looks like visually. That's a sideways parabola. So if you didn't know that, like, you could try plugging in points and seeing. So it kind of is written in a way that would tell you that. I don't know. How do I explain this? It's like you would set x, like imagine you take x is equal to some number like 4, and then you think what y values would solve this equation. Well, the answer is +2 and -2. And so then you end up plotting 2 different points, and then you can see, like, tracing it all out, that you've got a sideways parabola. Oh, and it's saying x equals 4. Okay, so x equals 4 is actually the upper function. How do I want to? Maybe I'll just say x equals 4. I'll label it like that. Okay, so this is drawing the region, and we want to revolve this around the y-axis. Okay, this whole thing is actually the region we're revolving, and this is where well, we have to kind of tilt our head sideways. We have to realize that the segment that we want to revolve to set up this problem, it needs to be this. It needs to be perpendicular. In fact, if you try to make it parallel, like, you'd run into a problem, because it's hard to, like, say going from one end to the other, and I don't know if it's even possible to set it up that way. Maybe it is, probably is, but this way is the most clear way of doing it. Okay, so we need to make that red line run from the different ends of our integration. So this is where we need to think about when do these things intersect, and I actually have already said the answer, +2 and -2. All right, that's where it intersects with 4. Okay. All right. And so this is going to be washer method, since there's a upper function and a lower function. All right. There's a gap between the lower function and the x-axis. It's another way to, or the axis of revolution. That's a different way of thinking about it. And so washer method, and we just set things up according to the equation or the formula. So big radius in this case is going to be just the 4 squared. And the small radius is going to be the y squared function. So we end up squaring that. And now we integrate this with respect to y, because our red line in this case is varying over the values of y. So you can anticipate that this should be phrased in terms of y. All right, now we just go ahead and compute this thing. First I'll simplify. Okay, and now we just compute it. Well, if I'm computing the integral, I don't need to write it again. So 16y minus y to the 5th over 5. Evaluate from -2 to 2. Well, and then you can plug this into a calculator or something. You could also compute this by hand, but it's just a bit of a bother. You'll get 128 over 5 and minus -128 over 5. So you end up doubling them up. You get 256 over 5 pi. Okay. All right, and I want to leave the next 2 pages for next time. So I guess this will be our last problem for today. Okay, so find the volume of the solid rotating this region bounded by the exponential function y equals 1. And okay, so the important thing about this problem is actually that the axis is not one of the standard axes. It's instead y is equal to -2. So we're going to see just how much this affects disk/washer method. So the exponential function, you should know, looks like something like that. And y equals 1. Y equals 1 is going to be somewhere up here, because this intersection point is, well, no, this intersection point is y equals 1. This is supposed to be asymptotic approaching 0. And this is y equals 1. So we can draw a horizontal line here. And x is equal to 1 is going to go up to e. So, right, okay. Yeah, so if this is 1, then this point would be the value e. And so the region, maybe I should have drawn this a little bit larger, but it's that little triangular looking area. And we want to revolve this around y is -2. Okay, so let's just try to be a little bit accurate. Computer's slowing down. Okay, so this is our axis. And we want to revolve around it. So let's think about the formula. I guess I'll rewrite it. So it's big R of x, which we would then square, minus little r of x, which we also square, and we integrate that, and we have a factor of pi out in front. Okay. So what happens is that the radius formulas are not necessarily going to be just the formulas given to you, but they have like you have to like add or subtract. You have to tack something on to denote the fact that the axis of revolution has been shifted away from the standard. Okay. So maybe I'll just try to draw like this would be where the normal axis is, and then the dotted line is where it actually is in this problem. But we still have 0 to 1, right? That's still, and we have dx. We know all of this is true. For the big axis, so I guess what we need to do is, yeah, this is how I'll explain it. Yeah, so this distance is 2. And that's how much we've added on to the distances, the big R and the little r. So what you want to do in this problem is you just want to add that shifted amount. So we want to add, oops, I don't really want to use a different color. So we have e to the x as our upper function, and we add 2 to that distance because it's, well, because we shifted the axis of revolution away by 2. And then that's the new radius, that's the new big R, and we square that. And we then subtract off, well, the small radius function would be given by x or y equals 1, which is just the function 1. But we have to add 2 to that, and so we end up squaring that. Okay, and then we can compute this. So I have to simplify it a little bit. And one thing here is that e to the x squared, you can end up rewriting this as e to the 2x. That's just a exponent property. When you raise something to a power and then to another power, that's the same as multiplying the 2 powers together. All right, and then 2e to the x, not 2, 4e to the x. 4e to the x plus 4 minus, and then 9 dx. Okay, and so then we integrate this guy. So you'll have 1/2 e to the 2x. This is a simple u sub if it's not immediately obvious. And then this is going to be -5. So then when you integrate, you get -5x. Yeah, and then evaluate from 0 to 1. And lastly, when you do that evaluation, let me see, how bad does it get? It's not too bad. Plugging in 1, you'll get e squared over 2 plus 4e minus 5. And when you plug in 0, you get, maybe I'll make this a bracket, put a parenthesis here. So plugging in 0, for the exponentials, it doesn't completely kill them. So you have to keep track of things still. Minus 1/2 plus 4. And so the e squared and the e are going to be fine. You have -9 minus 1/2, so -19 over 2. Yeah. So e squared over 2 plus 4e minus 19 over 2. And that's what I had from before. So yeah, good. Okay. Right. So are there any questions on this material? Okay. Well, so I'm not hearing anything. I guess we can stop